I'm Petros Gigis. I'm about to defend my PhD very soon. And today I'm going to talk about why we think there is value on being able to detect non-spoofed traffic at ISP Ingress points. And to begin with, let's see a simple topology consisting of three ASs. AS2 is a customer of AS1, and AS1 is a customer of AS3. And let's take the perspective of AS1. In this simple topology, AS1 expects traffic with source IPs from AS2 to traverse their direct link as this generates profit. However, maybe due to misconfiguration, or maybe AS1 failed to advertise the route to AS2, the traffic may follow a different path. And instead of reaching through the direct link, now it comes through the provider AS3. And in that case, AS1 can rely on technology like SFlow, NetFlow, look on traffic levels, and detect that something doesn't look right. But in reality, what can happen is that maybe spoof traffic with source IPs of AS2 comes through AS3. And in this case, if AS1 decides to troubleshoot this as a network issue, it will start troubleshooting something, but it's not a routing issue. It's just spoofed noise. So the question that comes to our mind is how we can distinguish which case we are in. And our idea is that we can look for legitimate traffic. And by legitimate traffic, we refer to non-spoofed traffic. And legitimate traffic is usually originating from where it claims to be from. So what we can do is that we can look for non-spoofed traffic, legitimate traffic, and we can use it as a routing signal. So if we're able to detect non-spoofed traffic at the ingress point, we are sure that there is at least a valid routing path between the source and our monitor. So packets arriving through a valid path. And the big idea here is that imagine that you are a trans network and you are able to detect non-spoofed traffic at your ingress points with very high accuracy. Over time, you can start building a database of what looks normal. And with this map of where each source prefix is set in your network, you can use it as a baseline when things start not looking normal. Any deviation from this picture of normality can be a routing incident, but also it can be a valid change. And we consider that being able to detect non-spoofed traffic with high accuracy can allow network operators to detect BGP hijacks, route leaks, but also detect other cases such as unprofitable paths, like traffic taking expensive transatlantic paths. And the question here is how we can distinguish non-spoofed traffic from spoofed traffic. And let's see an example of a POP topology. We have AS1, AS2, and AS3. And let's say that we are interested in traffic from AS3, but it's ingressing in router 3 of AS1, and then goes to the rest of the backbone of AS1. So our deployment scenario that we have in mind is that we can install a middle box which runs a checker, and the checker tries to distinguish non-spoofed traffic from spoofed traffic. So what is happening is that the moment of the traffic that we're interested in, and it comes in a location that we didn't expect, we slice a part of it, we send it to this checker, and then we forward it back to the network. And the other important question is how we can distinguish non-spoofed traffic from spoofed traffic. And this is not easy, but there is a difference between spoofed traffic and non-spoofed traffic. And the difference is that spoofed traffic is unidirectional, while non-spoofed traffic consists of at least some closed-loop flows. And by the term closed-loop flows, I refer to flows that the sender sends some data to the receiver, and the receiver sends some form of acknowledgement to the sender in order to send more data. And TCP by default is a closed loop protocol. Because in TCP, we transmit some data, we get the acknowledgement, and we send more data as part of the reliable data transmission. So during my PhD, I developed a proof of concept algorithm, which is a probabilistic algorithm. And this algorithm interacts with TCP flows. We track the state of TCP flows, and randomly, we drop a few TCP packets. We drop data packets. And based on the outcome of our packet drop, if we observe a transmission or not, in our model, we get confidence on the hypothesis, is the traffic non-spoofed or it's spoofed. But also it sounds very simple, okay, we drop a packet and we wait to see the retransmission. There are many things that may go wrong. And this is very important to have a very high accuracy when we classify traffic as non-spoofed, because we don't want to create a system that has a lot of false alerts and becomes unusable. So we want always to make it correct if the traffic is non-spoofed. And some things that can go wrong is part of the network conditions. For example, we may have packet loss, some other things that are not all TCP implementation stacks are the same, but also there might be an adversary that knows exactly how our algorithm works and wants to bypass it by sending duplicate packets in order to mimic retransmissions for our packet drop. And we found in our evaluation that if we drop 12 packets across hundreds of flows and across thousands of packets, we can get a very strong signal on the nature of the traffic. In that case, we found that the best attacker strategy to bypass our algorithm is to just send duplicate packets under our threshold, which we assume a 15% duplicate threshold. And in that case, the chances to misclassify spoof traffic as non-spoofed is 1 in a million. And another interesting finding was that even in cases where we have mixed traffic, we have non-spoofed and spoofed traffic, we are still able to detect non-spoofed flows. And finally, as we have some mechanism in order to decide which packets are considered as droppable or not, we found that our technique is adding a very small impact to the TCP completion time. And all of these mechanisms, if you are interested to read it in detail, they are described in our paper. And I hope that I have convinced you by now that there is some value of being able to detect non-spoofed traffic with high accuracy at ingress points. As currently, thanks to RIPE-NCC, we are building an open source version of our proof of concept. And in this open source version, we have 2 modes. The first mode is the one that I described. So we slice a part of the traffic, we send it to OpenPenny, and OpenPenny drops a few TCP packets. The number of packets that OpenPenny drops is configurable, so you can get away with 3 to 5 packet drops and still get a very strong signal. And the second mode that we have thought is that a passive mode, where in this mode you don't have to slice traffic and send to the middle box, you just mirror traffic. And as our algorithm tracks the TCP state, we can detect packet loss if it's upstream, downstream. We can detect if there is long balancing per packet, but also we can detect if there are TCP flows that have been arbitrarily terminated. And the main takeaways that I would like to conclude with my talk is that I think if we are able to detect non-spoof traffic with high accuracy, we can build systems or integrate already systems, and we can use it to identify routing incidents such as misconfigurations. And in our algorithm, we just drop a few packets across thousands or millions of packets. And we think that this can give us a very strong signal on the nature of traffic and it's cheap in terms of the impact that we have on the traffic. So the current status of this work is that we are moving from a proof of concept to an open source version, but it's going to be available later this year. And again, thanks to RIPE-NCC and this community-funded project initiative. And by concluding with my talk today, I would like to ask you if you have other use cases for such a technique. Thank you.
Thank you, Petros. That's really good. Have we any questions? I think we have one at the back.
Yes. Hi, Greg Choules, ISC. Is this only applicable to TCP at the moment or other transport layer protocols?
So far, we have considered TCP because the header on TCP is unencrypted and we can distinguish retransmissions. But we have thought also about QUIC. And the main problem with QUIC is that we cannot distinguish if a QUIC packet is a retransmission of a packet that we drop. But we have thought of becoming a bit more aggressive. And instead of dropping a data packet of a QUIC, to drop the initial QUIC packet. And we expect this to trigger the application to send one more retry, but it's going to cause more impact than just dropping a packet while the connection is already established. And the other scenario that we have in mind about QUIC is that there are some firewall vendors that they describe that because you cannot do deep packet inspection in QUIC, just drop QUIC traffic, which is it's considered a bit aggressive, and then you expect the applications to switch to TCP. But primarily, this work is on TCP flows. We expect that for the next couple of years or decades, there will be still some TCP traffic ingressing through ISPs.
Okay, I guess by definition, you can't really do this with UDP because it's not a closed flow.
Yes, with UDP, it depends on the application, and then it's a bit unpredictable. We have thought about TTL values, but still, if you have a sophisticated attacker, it can come up with different strategies of mess up with your implementation and try to cause you to trigger a false arrest.
Okay, thank you.
Nice discussion. Any other questions? I think we're good. Thank you very much again, Petros.
Thank you.